Well, hey, stats class. Thanks for being here today. We finally get Chapter 11 PowerPoint and video loaded up for you. I'm wondering if I might be able to get all of this done in one fairly good, solid, short little video. This is Chapter 11. We've already worked through a whole lot of hypothesis testing theory in Chapter 10. Now we get to some practical type things. Not practical, I guess just a whole lot of actual nuts and bolts doing some tests. So we're going to learn several more of them in this chapter. So let's see what we can do with them. The first section is an inference about two population proportions, when you go to let me trust the slides. Objective 1, distinguish between independent and dependent sampling. So there are a couple of different ways you can sample things. You can take a collection here, take a collection here. Sometimes those depend upon one another. Sometimes they are completely independent from one another. Think back to the independent versus dependent discussions we had way back when. The likelihood a randomly selected 40-year-old woman is going to survive the year. How about two randomly selected? How about two randomly selected in an apartment building, right? They are a little bit more dependent upon one another. So it's independent when one sample does not dictate the others. It's dependent when one does determine the other one. And matched pairs is what this is talked about a lot. I think we get to that in section 2 of chapter 11. And you can be matched actually against yourself. So that's an interesting topic we'll talk about more. Here are a couple of examples. A researcher wants to know whether the price of a one-night stay at a Holiday Inn Express is less than the price of a one-night stay at a Red Roof Inn. She randomly selects 8 towns where the location of the hotels is close to each other and determines the price of a one-night stay. Is that independent or dependent? How about a researcher wants to know whether the state quarters introduced in 1999 have a mean weight that is different from traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and compares their weights. What do you think? Are they dependent, independent, one of each? Which one? Well, the first one, it is dependent because the Holiday Inn Express can and actually must be paired with a Red Roof Inn by town. You can't select a Holiday Inn and have it compared to a Red Roof Inn in the same town if there is no Red Roof Inn in that town, right? So your choosing of these 8 determines how you choose these 8, and they are paired actually by cities. The second one, there's no bearing. You can select any handful you want, state versus traditional, and the difference in the numbers is actually your biggest clue there. But you picking a Delaware quarter does not mean that you're going to pick a 1985 traditional one. There's no bearing one or the other. All right, so now let's test hypotheses regarding two proportions from independent samples. And if you remember last chapter, we compared a sample to the population. We were wondering, hey, here the population is this. Here's a sample. How does this sample compare with the population? Now we actually move to comparing samples within the population, which is kind of an interesting way of doing things. We're comparing, and a lot of times we don't know stuff about the entire population. We can figure out a lot about the individual samples and see if the two samples agree with one another. It's going to be proportions. It's going to be a 2-proportion z-test. The samples will be large enough, and we'll be able to do a standard z-test, not a t-test. The previous test, the population parameter was always first, and the null hypothesis was always the proportion equals the population. Here it's a little different because neither one of these statistics is a parameter. Neither one is more important than the other. So which one goes first doesn't matter. but it will matter in the homework questions because the researcher or the homework question will have established which one is first. So make sure that you know which one is first. If this one is greater than this one, that means this one is less than this one if you have them switched, and the tails will be a little bit wrong. Just be very careful, like all the other questions of the homework have forced you to really read carefully. So just make sure that you're careful about that. You don't want to see the formulas. I'm sure they're in your book. We're just going to be working with z-scores to determine how likely it is these two proportions are similar. And the technology is going to handle it, provided we point the technology in the right direction. So let's use the multi-step method to address this. An economist believes the percentage of urban households with internet access is greater than the percentage of rural households with internet access. He obtains a random sample of 800 urban and finds that 338 of them have internet. He obtains a random sample of 750 and finds that 292 of them have internet. Test the economist's claim that urban is greater than rural at the 0.05 level of significance. So we're going to have several steps. I do have the PowerPoint loaded up for you to see. And what's interesting is when we go through this test, of which we now have three, one proportion, one mean, here's two independent proportions. It's a z-test. How do I know it's right tail? And that's one of the first things we do, right? Actually, what is really beneficial is if we establish very clearly in step 2 that we're going to let our first proportion be urban and our second proportion be rural. Why? Well, because that's the way we saw it in the problem. There's no reason to switch them. We'll just keep it straight in our own minds and in this problem as well. So urban is first, or rural is second. And I believe the researcher was considering that, didn't the researcher believe that urban is greater than rural? So if urban is greater than rural, then the first is going to be greater than the second. What is your null hypothesis? The null hypothesis is a statement of equality, that they are equal to one another. But I want you to notice something here that StatCrunch does, the book also does, and consider this comparing things to 0, which I kind of like. If these two are equal to one another, then wouldn't their difference be 0? And if the first proportion is greater, then when you subtract them in this order, 1 minus 2, you're going to get a positive number. Now, it just so happens as I work through these slides, most of them happened to be right tail tests, and I apologize for not mixing it up a little bit. But if this had been a left tail test, you'd still have 1 minus 2, but it would be less than 0. It would be a negative because you'd be implying that the first one is less than the second one. That should make sense to you. But that then, if this is a greater, first greater than second, that would explain why working backwards we can see that this is a right-tailed test, because we're talking about things that are greater than. All right, so step 3, our level of significance, just about always is going to be a 5%. And now the critical values, you know how to look up the tables to find, there's the small little table for z-scores. Right, and that is our boundary mark. And maybe at this point you're relying a little bit more on the probability result of the test, comparing that to alpha, rather than going through. And that's fine. If the book is not forcing you to find the critical value, blow over it and jump right to the probability, comparing that to alpha. That's a much more efficient way of doing things, especially with the t. The t coming up with on that chart with the degrees of freedom. Some of the degrees of freedom stuff is a mess. So use the probability. That's a very efficient way. But regardless, if the question asks for it, we need to be able to find it. And that's the small little chart. This is a right tail, 5%, 1.645. And then we can go to our StatCrunch. And in the StatCrunch, it's a 2 cent. I think maybe I'll show you this one real quick. This is a later one, so ignore what you're seeing here. I'm going to duplicate this. If you go to a z-stat 2 no, sorry, proportion stats, to sample with summary, then you get exactly what you saw right there. And you notice that they have the difference, the P1 minus P2 equals 0, and the P1 minus P2 you've got to set at greater than. And that's what I have right here. I put the successes in as the fraction, and then equals 0, greater than 0, and we move on and see what our summary statistics are. I always check the graph to see a graph, and by seeing the graph, it'll show me, confirming that it's a right tail, showing what the z score is, the test statistic to compare to the critical value, along with the probability. And wow, that seems like a pretty big region. It's a pretty low z-score. It's a pretty high probability. What does that seem to do? We make notes of those, and it seems that z is inside that boundary. So we're gonna fail to reject this. In other words, we're going to accept the null hypothesis. I know accept is the bad word. We're gonna fail to reject that, which basically means what? The p-value is greater than a. The data is your evidence that the sample proportion is not statistically significant. There's not sufficient evidence to reject, so you should fail to reject it. What is our really cool conclusion? There is insufficient evidence to suggest that urban households have more access to internet than rural households. That seems to be the case. If you are out there in the Pine River District wishing that you had something other than a hotspot, I'm sure you might have something to say about that. But maybe it's the fact that you have a hotspot, which is why rural and urban households seem to have about the same. Of course, this is probably dated info anyway. Those proportions were pretty small. How is it that, I mean, most places have internet these days? But that is the process, and I hope that makes sense. Now, here's another way that we could make a test. Here's another way we could have a test. And I think I can draw something. We can construct confidence intervals. Let me that previous data, right? What was the I'm sorry, what were the numbers? $338 over 800 is approximately equal, and 292 over 750 is approximately equal. So 338 divided by 800 is 4225, and 292 divided by 750 is 0.3893. Now, we would all agree that this is a sample of urban. This is a snapshot point estimate. The real value for urban is somewhere between these two values, with 0.4225 in the middle, right? We can make a confidence interval, right? Would you also agree that this is a snapshot, a point estimate of the rural? Well, this rural is less, which means this confidence interval is going to be somewhere over here. But the question is, if it's here, we could probably agree that this one is greater. But what if there's some overlap, right? What if it looks like this? And we can see then that, of course, the 3893 is less than the 4225, but with the wideness of those confidence intervals, there's going to be some overlap, right? So keep that in mind as you process through this whole idea of confidence intervals between two population proportions. Okay, so I'm thinking of two numbers that are the same. Subtract them, what do you get? 0, right? If I'm thinking of 5 and 5, when I subtract them, I get 0. If I'm thinking of 9 and 9, subtract them, I get 0. What if they're not exactly the same? What if they're really close to the same? And if they're close to the same, then when I subtract them, will I get a number close to 0? Either a small positive number, a small negative number, or maybe even 0 itself, right? So the difference then needs to be close to 0, including something negative and something positive. And that's the whole idea, kind of what I've said right here. If we're setting up a confidence interval for the difference between two numbers. So let's say that I take a random number from here and subtract it from a random number from here. Sometimes this number might be larger than this number. Sometimes this number might be smaller than this number. And when I take every number from here and subtract it from every number from here, will I sometimes get positive? Will I sometimes get negative? Will I sometimes get 0? Now, if I have two confidence intervals like this, if I take every number from here and subtract it from every number from here, will I ever get a negative number? Will I ever get 0? No. And because I will never get 0, I can say that these two numbers are different. They are statistically significantly different. Whereas here, as we've already shown from our previous hypothesis test, these are not different. And we can construct a confidence interval that shows that when I take all of these and subtract all of these, I'm going to sometimes get positive, sometimes get negative. And that is the thing. So when I set up this confidence interval with those two things, if my interval that I create, the single interval I create, if it includes 0, then we can reasonably expect that the two numbers are statistically the same, statistically similar. Okay? So, okay. So the process is similar. Everything in that multi-step method is the same, but we're just going to select a different option within the test, making sure we check our level of significance. So, our previous example, steps 1, 2, 3, 4 are the same, but step 5, instead of clicking hypothesis test, I just click confidence interval for the difference. And my level of significance is whatever my alpha is. My alpha is 5%, and level of the confidence interval is going to be a 0.95. I included the confidence interval plot just for fun so we can see what it looks like. Here's our first screen. And look at this, the lower limit, upper limit. What do you see there? Maybe you can't see it. It's a negative. What do you see here? It's a positive. And because it goes from positive to negative, and in this plot right here, because 0 is within this interval, I know that they are statistically similar to one another. And if they're statistically similar, that means there's no difference. And if there is no difference, then I can't reject the null hypothesis. Okay? So that's how we can do those two things right there. All right, that is, boy, that's a 19-minute video right there. I'm going to have to stop it. Okay, so that's section 1. Section 2, please watch section 2. I'll try to make sure that it's a shorter one. The matched pair stuff really works different than anything that you would expect. You'd expect StatCrunch to work a certain way. So hang on for this next video.